Okay, so where were we before the break? So we were looking at this relatively simple example of trying to compare the means of three different samples, all right? And we said we're going to use ANOVA, so we're just kind of discussing the variance part of ANOVA. So we said, let's remember what variability and variance are. And I will use these terms sometimes interchangeably to refer to the dispersion. But there is a reason why there are times where I'm talking only about the variability and not about the variance. And maybe I'll discuss that next week. All right. But you'll hear me saying variability, you'll hear me saying variance. When I say variability, I mean sum of squares. When I say variance, I should mean the mean squares, which is the mean variability. Okay. Um, why we sometimes prefer one to the other, again, it'll be a discussion for another time. So we said that what variance is, ANOVA is going to do is this little trick where it's going to ask, is the variance of this system of data that we have, these multiple samples, is it bigger than it would be if the means of the three data sets agreed with each other? All right. So that way it doesn't have to make multiple comparisons of multiple means. It can just compare two things. All right. And it basically breaks down the dispersion into two aspects of the treatment. How much difference was caused by introducing treatments, and how much of this is just because of the error in the data, like the wobbliness of the data alone. All right. So let's take a more concrete look at ANOVA and the math behind it, and let's try to get a sense of the intuition behind it. Okay. Now, just a little um, reminder that ANOVA has some requirements. ANOVA does assume that the the samples you're getting for the different treatments, they come from populations with normally distributed data. All right, so that is one of the assumptions of ANOVA. Um, the other is that the variance of the three treatments is the same for all the treatments. All right, they should not have completely different variances. There are ways to make this more robust, but this is the basic assumptions of ANOVA. And that the response variables are not related. We may be talking about these two a little bit later, but this point that the observations are independent basically means that we want to ensure that these three advertising strategies, they didn't affect each other. Okay. Oh, question. Yeah.
I have a question. In the second requirement, it has to be exactly the same, or can be like really close to it, like the variance.
Ah, it cannot ever be exactly the same. You can never have two samples with exactly the same variance. But you might want to see if they are close enough that you cannot dismiss the fact that they may be similar. That's a very long and complicated way of saying you might want to do a test of variances. All right, you might want to do like a F test of the variances to see if you can say that they're similar or different. Okay, all right. Um, so the last point, though, about the observations being different, independent, it means that these three treatments should not have affected one another. Now, this class is more about computation and less about design of experiments, so I'm not going to go further into that. But there's all kinds of problems associated with doing real-world experiments that this last observation is very hard to ensure. For example, let's say we did do three advertisements in three different cities, right? What's stopping your friends from another city calling you and saying, hey, did you know this product is now on sale? Or something like that, right? And they can contaminate each other, all right? So there's many ways in which this last assumption is very difficult to ensure, and that's where a lot of the skill in designing experiments properly goes in, all right? And we're not really talking about that right now. But ANOVA is somewhat sensitive, but not overly sensitive to these requirements. Okay. Um, okay. So I mentioned earlier that it's going to be breaking down the variability and variance in our data to examine it in different and interesting ways. Let's take a look at some of those ways. Okay. So it's going to essentially compute two types of variance. Let's look at them one by one. The first variance is how much of this variance is because of the treatments and is the difference between the treatments. All right. So this is the first kind of variance it looks at. It's called MSTR, or mean square due to treatments, or simply treatment variance. All right. And what it does is it takes, let's see what it does in the numerator here. Here, it's comparing the mean, this x sub j is comparing the mean of the three treatments against the grand mean. Okay, it's looking at the difference of each mean from the overall mean. All right, and it's squaring it, it's multiplying it by how many, by the size of each treatment. But the essential point is it's getting some kind of information about how much deviation there is from the mean of the samples from the mean of the entire data. All right. So to go back and look at our original picture up here, that numerator is the difference. Well, this is the median, but imagine the mean is close to here. It's the difference from the mean to the grand mean. The grand mean meaning the mean of all the data. All right. So it's this difference versus about this difference versus about this difference here. Okay. And it's aggregating these differences. As you can see, if our three treatments were very similar to each other, the difference of each mean from the grand mean would be much smaller. All right. Or maybe even zero. I don't know. So this variance is really picking up how much variance is there because the treatments are different from each other. All right. And the way it's looking at it is by comparing the mean of each sample to the mean of the entire data, all three samples combined. All right. The bigger that is, the bigger this variability will be. Notice the numerator here is a sum squared expression. Okay. And it's the sum squared of the treatments. It's the variability due to the treatments. All right. By dividing by the number of treatments we have, we're taking an average variability, which is a variance. So this is the variance due to treatments. All right. It's going to look a little bit different than other maybe variance formula you have seen because it multiplies by it. It goes through this sum. It sums three numbers, and each sum is for one treatment, and it sums the squared deviations by the size of each sample. So essentially, if your samples were of different sizes, this takes into account. It weights them differently. Okay. All right. So that's the treatment. So that gives us the variability of the treatments. This gives us the variance due to treatments. Right. Notice here the K is the number of treatments that we have. Okay. All right. The other variance it looks at is called the within treatments variance. It's asking how much variance is there within each treatment. Let's not separate the three treatments, just within each treatment, how much variance is there. All right. So in this case, we're looking at each of these independently and asking how much variance is there in this treatment, and in this treatment. Ignore the fact that they are far or similar to each other. All right. So what does it do? We start by just taking this s squared is the s is the standard deviation, s sub j is the standard deviation for a particular treatment. S squared is the variance of that particular treatment. Okay, so it's looking at three treatments, j from 1 to k. For each treatment, it's looking at its variance and it's multiplying it by its degrees of freedom. Effectively, it's getting its variability. Because remember, variance is variability divided by degrees of freedom. So if we take the variance and multiply by the degrees of freedom, we are removing the denominator of the variance and we end up with a variability again. So it's actually looking at the variability of the three um, treatments, okay? It's ignoring the fact that they each have different means. It doesn't care, all right? It's just looking at the variability of the three treatments, and then it's dividing by this expression, which is the total amount of data you have minus the number of treatments you have, okay? In a later week, we will come back to why degrees of freedom have such strange expressions like k, n minus 1, k minus 1, n minus k. Like, what's going on here? All right, we'll come back to that when we have a more geometric sense of data. We'll come back to asking this question because what degrees of freedom is can be a little bit better understood when we understand the geometry of data a little bit better. All right. Um, so what's the denominator? Well, what's this expression doing then, essentially? So what it's doing is it's looking at these three treatments, but this time it's ignoring that they might be very separate from each other, and it's asking what is the, on average, what is the variance of these three treatments? All right. So it's asking how far is the data of each treatment from its own treatment mean. It doesn't care that the treatments have three different means. All right. So why is it doing that? That variance, the variance of each treatment from its own mean, is the error variance. All right. This is not this variance is not because we had treatments, it's because of everything else. It's because of the other noise in the data, in the world. Okay. It can be because some people read the advertisement carefully, some people don't read it carefully, some people ignore it, etc. All right. So if you take just each treatment one at a time, its variance is kind of considered like an error variance. It's not because the treatments are different. And when we take the average of these three variances, we're getting a sense of what is the average for each treatment, ignoring the fact that they are different treatments. Okay. So in a sense, this first variance up here is asking how much variance is there because the treatments are actually very different from each other. And the second variance is kind of like, what would the variance of the whole system be if the treatments were not different from each other, right? If the treatments were relatively similar, we ignore the fact that they have three separate means. They still have some variance because they have data in them, right? So what is the difference between this picture up here and this picture down here is effectively what it's asking, all right? If the three treatments had no difference from each other, they would look like this picture down here. So then what we do is we simply take these two variances and we divide them. If the treatments didn't have any effect, your data would still have some variance because of error. It would look like this second picture. And the variance of the treatments, if there was no difference between the treatments, would be the same as the variance of the error. All right. So essentially it's saying if the treatments had no effect, the numerator and the denominator would both look like this. And therefore, the F value we would expect if the treatments were not different from each other would be 1, right? It would be 1. Because the variance in the system would be the same if there was no difference due to treatments, all right? So that's essentially what we're doing. ANOVA is doing, it's taking advantage of this property of the F distribution by comparing two variances, all right? And that's a quick and dirty recap of what ANOVA is. I've got a little couple more slides just explaining the same thing again and again, all right? So essentially it's asking this question. It's saying you've got three samples, right? each from a different treatment, and they have an overall variance, overall distribution that looks like this, let's say. That's the dark line here, okay? If the three treatments were the same, they didn't have much of a difference from each other, the picture would look closer to this, where the variance of the whole system would be similar on average to the variance of the three treatments. All right. So it's asking, is the variance between the treatments greater than the within treatments variance, or is it the same? The within treatments variance is the average variance of these three smaller curves, the average of them. All right. So that's essentially what it's asking. Here's the same story one more time. So the between treatments variance, what is it really doing? It's looking at the, and I'm kind of drawing in blue like two different treatments. I know there's three, but let's look at two at a time, okay? So I'm looking at two, and it's taking the difference from the mean of one treatment to the mean of the whole data. Whereas in the within treatments variance, the MSE, or the error variance, is just looking at the variance of each data point from its own mean within its own treatments. Okay? And if it's saying if these two variances are similar, then there is no effect due to treatments. So then it puts the treatment variance in the numerator, which should be at least as big as the error variance, but significantly bigger if the treatments have an effect. And the error variance in the denominator, okay? And then we have our F statistic. So we should expect values close to 1 if the treatments are not effective. All right. And is that what we get? So we can do this a long way. I know there's an F-test function built into R. You guys have caught on to me now, but I'm going to do it the long and dirty way, all right? Just to kind of see that we know how to write this code, all right? So here's the code to do it the long way. And I might ask you to do this on your homework one time, just so you can convince yourself you know how these things work, all right? One of my goals in this class is that I don't want you to get out of this class only knowing how to run R functions. I want you to feel confident that you can dig deep and recreate some of these by yourself, all right? Because the time may come one day when you have to write one of these things for yourself because certain assumptions are not met or something like that, okay? Okay, so treatment variance. Wow, what an ugly formula, but we can write it out by ourselves here, all right? This expression here is the mean of a treatment. I can get the mean of all three treatments just by doing that. We saw that before, right? This expression here is the grand mean. It's the mean of all the means. I can get that by just taking this expression and taking the mean of it. I can just take the mean of that whole expression. It's the mean of all the means. All right. So I've got this little part in the middle figured out now. All right. Then I want to square all those differences and sum them up and multiply them. I need to multiply each of them by the size of each treatment, but they all have the same size, 50, so I can move that outside the sum expression. Okay. The degrees of freedom is simply k minus 1 is the number of treatments minus 1. So our treatment variance is this final number. Okay. You'll notice the variability, the treatment variability is a much bigger number. But after we've divided by the degrees of freedom, our variance is a smaller number. It's like the average variability of the three treatments. Okay. From the mean, the variability of each treatment from the mean on average, from the grand mean on average. All right. The error variance is simpler. It's it can be computed by simply taking the degrees of freedom for one treatment and multiplying it by its variance. So here is the variance of the three treatments multiplied by their degrees of freedom, and we just sum it up. Okay. The denominator is the total size of our data, which is 50 times 3 minus the number of treatments. And then we can compute our error variance. So our error variance, you notice, is very small compared to the variance of treatments. This F statistic, will it be close to 1? No, it's going to be really far from 1. It's going to be a really big value, right? Once again, you notice the variability within the treatments is a big number, but there's just enough data to make the variance a much smaller value. All right. The F statistic is simply the two variances divided by one another, the bigger one in the numerator always. All right. And that gives us an F value of 108. That's quite a bit bigger than 1. Yeah. So we can compute the cutoff value for a F distribution like this. The cutoff value, the 95% cutoff value is, with these two degrees of freedom, is about 3. So values bigger than 3 look suspicious. We begin to say we don't believe the null hypothesis anymore. Our value is bigger than 3. Our F value is 108. We can compute our P value. It's simply this using the P function, and it's pretty much 0. All right. It's unbelievably small. All right. So this is the long way of doing ANOVA. I do want you to type this all out and just try it one time by yourself to show yourself that you really understand how ANOVA works, how it breaks the two treatments. Write the code yourself. So I'm going to ask that, I think, for your homework assignments. Okay. It's not hard though. It's not hard. One thing to note though, that the code and the math do look a little bit different because but they're doing the same thing. All right. Essentially, this sum is right here as a sum, and I'll be summing 3 things, right? From j equals 1 to k being 3. But I'm not writing a loop. I'm not writing a loop and then summing those 3 results together. Well, I am doing a loop, but it's a implicit loop. I'm using functional iteration, right? I'm computing this expression 3 times. I'm computing it by using this kind of, this returns to me a vector, and then this is a difference between 2 vectors, okay? Excuse me, it's a difference between a vector and a constant value. So this total difference squared is going to be a vector, and then I'm summing that vector together, right? Okay, so that's ANOVA. And if we go through ANOVA this way, we see that we can reject this hypothesis. We must therefore believe that the treatments are having some kind of an effect. All right. Here's ANOVA the easy way. Okay. Well, it's easy except for one thing. There's 2 functions that I want you to become familiar with. One is called one-way test, is what we just did. It's called a one-way ANOVA. And then there's another function called AOV, which is for more powerful ANOVA designs. All right. But you can get used to both. But I just want to show you a couple of nuances of using them that makes it that you should be aware of. Okay. First of all, remember that our data looks something like this with 50 rows, but I've only shown 4 here, right? We have 50 rows, but I've only shown 4 and 3 columns, right? Here's a problem. These functions, one-way test and AOV, they're expecting your code to look not like this, but rather like this. What's the difference between these two types of code? Not your code, your data to look like this. What's the difference? So the data that I gave you, or that we're seeing here, has got 50 rows, and each treatment is just a different column. It's the rational way of organizing your data. It's the way maybe somebody is going to like hand you the data and say, this is the data we got from the experiments. However, R is expecting the data to look like this. Rather than having the three treatments be three different columns, it wants the values of all the treatments to be in a column by itself called whatever you want to call it. In this case, let's call it sales. And the strategy you used to get each of these sales, meaning the treatment you used, should be a column by itself. So actually, it wants the data not in a wide format, but in a tall or a long format. Okay? Instead of 50 rows, it wants 150 rows, where the first 50 rows will be, two columns with the treatment number and the sales of that treatment. The next 50 rows will be the treatment value 2 with the sales for that second treatment, and so on for the third treatment as well. All right. So unfortunately, we cannot simply plug this data that I've given you into your R function. All right. It has to be reshaped. The shape of this data has to be changed. And I'll show you a couple of ways of doing it. As always, the hard way and the easy way. All right. But I'll only show you the hard way. So what we can do is, and there's probably better ways of doing this, but here's one simple way of doing it. Okay. So remember that our data is, let's look at it like this. It looks something like this. It's adverts with three columns, T1, T2, and T3. What I'm going to do is I'm going to take just the first treatment values. So this is the sales of the first treatments. Okay. And I'm going to repeat the number 1 50 times. We now have the two columns that the long form data wants. It wants 50 ones in a row, and it wants the 50 sales values. It wants 50 ones in a column and 50 sales values of that strategy in a column. All right. And what I'll do is I'll simply put them together in a data frame. And that's what it looks like. Here's all my sales numbers for the first strategy, for the first treatments, and the number 1 repeating 50 times. Okay. That's 1/3 of the data that R wants me to have. I can do this 3 times for the first advertisement, the second advertisement, the third advertisement. All I'm changing is the treatment numbers, and the sales numbers are coming out of the adverts data set. Okay. So ads 1 looks, ad 1 looks like that. Ad 2 looks like this again, 2 all the way down. Ad 3 looks like this, 3 all the way down. All right. So I've got 3 data frames, but what R really wants these data frames all stuck together, like one on top of the other. And I think you have seen this function in your tutorials. But what we can do is we can combine these 3 data frames and tell R we want to bind them together. Bind means we want to stick them together. Bind just means stick. We want to stick them together. And R means rows, which means stick them together row-wise. Okay, so keep the rows distinct. Don't stick them together left and right as different columns. Stick to them together as different rows. When we bind them together like that, then ads becomes a huge data frame with exactly the form we want. 2 columns. One is the treatment number or strategy, and the other is the sales for that strategy. Okay, so now it's treatment 2, and now it's treatment 3. You can see where the crossover. All right, at 50, at 100, they cross over to the next one. Okay, all the way down to 150. Just to show you in more detail what rbind does, if I have 3 lists, let's say this is a sequence 1 through 10, C2 is 2 through 20. Oh, no, not 2, excuse me, 21 through, 11 through 20. And C3 is 21 to 30. Okay, so C1, C2, C3. R bind C1, C2, C3. Stick these numbers together as separate rows. Okay. What if I wanted them stuck together as separate columns? Just C bind, yeah, you could guess. That's how it would look like. Okay, so R bind and C bind. Two helpful little functions to kind of help you take apart data and reshape them again. All right. And now I'm going to tell you there's an easier way of doing all this. What I've just shown you is such a common thing for data scientists to have to do to reshape their data. There's a whole package called Reshape, or Reshape 2 in this case, which does this kind of transformation for you. All right, just because it's so incredibly common. And I'm not going to show you how to use it. Rather, I'm going to ask you to go find out how to use it. All right, so there's a really nice tutorial on how to use Reshape 2. It explains the difference between wide data and long data, and then it shows you how to stick them together using functions like melt and well, it's got decast and like it's got other functions. It'll show you how to kind of reshape data um, simply, okay, with one command rather than taking things apart and putting it all together. There might be one command that can just do it all for you in one shot, but you'll have to read that tutorial to figure out how to use it. Okay. The reason I'm not going to show it to you in class is because a lot of resources for data scientists are exactly like this. They're online. They're meant for you to be able to learn. They don't take a whole, they're not like that advanced. They're meant to be easy to use. So I'd like you to kind of just be able to figure out how to use them by yourself. All right. Once our data is in this long format, we can use this one-way or AOV tests to kind of run our F-test. All right. So one-way test, you've got to set up, what you see here now is a model is describing that the sales are dependent on which strategy I used. So I take this long format data that I created called ads, and I say that the sales and the tilde marks the separation between your dependent variables and your independent variables. And it says that sales is dependent on the strategy that I used, I believe. Okay. We set this assumption of equal variance to be true, and we just run this one-way test, and that gives us our F value and our P values. Okay. As you can see, our F value is extremely large. There's no way that this is going to be, there's no way that we're not going to reject this null hypothesis, right? There is another function that does something similar. It's called AOV. It's more powerful, and I think we will see it maybe next week in class. And AOV is for analysis of variance, and it's got a similar form. You just say AOV, and you give it your model. Notice here, AOV assumes that this add strategy, which is the numbers 1, 2, or 3, if you don't tell it otherwise, it's going to assume these numbers are like continuous variables. It's going to assume that, like, 2 is better than 1, 3 is bigger than 2. But actually 1, 2, and 3 are just labels for these three treatments. These treatments are categorical. They're nominal. There's just three separate treatments. So I use this function called factor to tell R that these three strategies that it's going to find in this column, 1, 2, and 3, are just categorical variables. All right, so factor tells R that this is a categorical variable called strategy. 1, 2, and 1 is not smaller than 2. They're just called 1, 2, 3. I could have called them A, B, C. All right, and AOV performs the same analysis of variance. And if you get the summary of its return value, it'll show you something like this. This is interesting. AOV's output is kind of interesting because it shows you this is the treatment variability and variance and degrees of freedom. It's saying for the treatments, the degrees of freedom is 2. The sum of squares of the variability of the treatments is written here. The variance of the treatment of the between treatments variance is written here. Okay? Residuals is just another word for what is left over, or error in this case. Okay, I'll talk later in the semester about residuals versus error, but for now just think of it as error. Okay, and I'll talk about later why we don't call it error all the time. Residuals just means what's left over, or error in this case. And we see the error degrees of freedom, the error variability are under, this is sum of squares, but it means variability. All right, and the error variance, which we computed all of these a long way before. Right, in the previous slide we did this all by hand before. So it's computing the exact same things we did up here. The MSTR and the MSE, and the F value is simply these two variances divided by each other. And you'll see that here as well. The F value is now simply this number divided by this number. Right? And this gives us an F value, and the P value is right here. It's telling you the P value is smaller than, well, it's pretty much 0. All right? That's ANOVA. Yeah, question.
Well, we have to set the parameter equal to false.
Right. So I said that ANOVA does have this assumption that your variances are equal. There are other modified ways. There's ways to modify ANOVA with unequal variances. So you can do that by this. All right. Just to go back again to the assumptions of ANOVA. Right. So there is a way to kind of do this a little bit more robustly if the variances are not equal, the second assumption. All right. It does still, however, assume that the data comes from a normal distribution, that the three treatments should have the three samples should come from normal populations. That's requirement number 1. Okay. And as always, if you can't make this assumption, you can probably bootstrap to resolve this issue. Okay. And we're going to see that in just one moment. Yeah, question.
Can we just tell which means are different from the others from the result or we have to conduct
Yeah, you have to right. You have to conduct another post hoc test probably to see if which ones are different from each other. We'll talk about maybe the post hoc more next week. All right, and the week after. But it does raise this interesting question. If we end up having to do post hoc tests, what he's describing is we may have to end up just comparing the three means against each other to know which one's significantly bigger or smaller, right? If we have to do that, why are we doing ANOVA in the first place? Why don't we just do that right away? And then we don't have to do ANOVA, right? We'll come back to this. That is not your question, but I'm making that question. Okay, so that's my challenge. Do we even have to do ANOVA? If we have to compare the three means at the end of the day to know which one is bigger and smaller, why don't we just do like all those tests, right? Why don't we just do those 6 comparisons right away? Is there an advantage to doing this big overall analysis first? You may have to wait 1 or 2 weeks to hear the answer to that question. All right. Otherwise, you guys would just pack up and go. So I've got to keep you back. All right. So I want to try to bootstrap this thing, but I want to ask a little question before we bootstrap this. Okay. Um, what would it look? What does it? What does the world look like when f is equal to 1? Right. When if the treatment variance was the same as the error variance, what, which would mean like our f value would be 1 or close to 1. What would that look like exactly? There's two possibilities, and I want you to think about like which one is more reasonable. To have f be close to 1, would it have to look like this, where the three treatments, and remember again, the means are these dashed red lines now, okay? Not the thick line. The thick lines are the medians. So would the means, if they are exactly the same, if the three means have to be exactly the same for f to be 1? Or do the three means have to be similar? Could they be similar but not exactly the same and f still be close to 1? That's my question. All right. When we say that the three treatments are not effective, meaning they should have similar means, should they have the same mean, or can the means still be a little bit different? All right. I'm asking this question because when I bootstrap, I have to simulate the null distribution. So I need to know this to understand what does the null distribution look like. What does the world look like if the three treatments were ineffective? Imagine, and I know these samples are not very big, they're only like 50, right? So the means are quite different. What if these samples were like 50 million, right? I mean, when Facebook does an experiment on its platform, like maybe it changes the color of a button or moves a button around, it's got 1 billion people to test, or it's got like 6 billion people to test on, right? Like there's billions of people using Facebook. They're going to have very large samples, right? Maybe in the millions or tens of millions potentially, right? If the three treatments were completely ineffective, would the means be almost, would we expect the means to be exactly the same, or still there to be difference between the means? I'm going to try to answer this question with code because that's all I know how to do. All right. So, all right. So let's think about this. How can we simulate an example where the three means are exactly the same? One way to do it is to just mean center all the data we have, right? If we mean center each treatment one by one, I can give them exactly the same mean, the mean of 0, right? So let me do that. Let me take adverts for the first treatment. This is the sales for the first treatments. And I'm going to subtract from it the mean of the first treatments. Okay? Some positive, some negative. On average, the mean of the mean-centered treatments should be pretty much 0. That's your computer's way of saying 0. All right? It's to 16 decibels, it's 0. All right? So I can do the same for the three treatments. Now, the treatment 1, so the mean, and let me just apply on these three treatments, T3MC, the mean. So let me find the mean of these three mean-centered treatments. What happened here? Oh, not C. Should I make them a list? Yeah, that works. Okay. So I make a list of these three mean-centered treatments, and you can see their means are now 0, because by mean centering, the definition of mean centering is the mean is 0. Okay. All right. Whatever would have been the mean is now at 0. Great. So is that what my data would look like if these treatments had no effect, they would have the same mean? Well, um, I'm just going to set up my data the way that in the long form that I need, adds MC. Okay, so this is the new data in the long form, sales and strategy. Okay, I have some negative values now, but that's just because I've mean centered it. All right, and I still have 3 treatments, 3 different strategies. Let me run a one-way test on this. Look at my F value on doing an F test on this. What is that F value? 0. But I thought I will get an F value of 1 if the 3 treatments have the same mean. Shouldn't I? Apparently not. The F value is 0. This is a very unlikely situation for the universe to have. What should I get? Well, even if the 3 treatments were ineffective, my means should still differ from one another a little bit. Why? Because there is variance, there is error in our data. There should be error in our data, and that not only affects how far each data is from its own mean within a treatment, it also affects how the means are different. That same error variance affects the means as well, and they will be a little bit different. Okay? To simulate what the world should look like if the treatments had no effect and they were producing the similar results, I cannot simply subtract everything from its mean to give it a perfect mean centering. Instead, what I need to do, and I'm going to set a seed here, is I'm going to do what I did before, which is mean center, but this time I'm going to resample from the mean centered data. Okay, I'm going to resample from this mean centered data. When I resample from it, its mean won't even be close to 1 anymore. All right, it will not be 1, excuse me, this mean will not be 0 anymore. It'll diverge a little bit from 0, the way nature does. All right, and I'm going to do this 3 times for the 3 treatments. And let me just quickly find their 3 means. S apply, and I'm going to take a list of treatment 1, mean centered, and resample. The RS is for resample, the MC is for mean centered. Okay. Excuse me. T2, T3. Okay. And I'm going to apply the mean to all these. You notice I've got non-zero means now. All right. If the 3 treatments were not effective, they would not have exactly the same mean. They would still diverge from the grand mean due to error. And that's what I need to model if I need to model the null distribution of F. All right. So I'll do this. This time I'll get values of F. I'm using a particular seed that gives me a value that's not exactly 1, but I get F values closer to 1. At least they're not like 0.0000000 something. They're going to be somewhere between 0 to 2. On average, they'll be around 1. All right. So just a reminder, I'm doing this exercise for 2 reasons. One is I'm building up what will become my model for the null distribution of ANOVA. But the second reason is just to remind you that ANOVA is not testing if your means are exactly the same. It's not testing if your means are exactly the same. It's testing whether these 3 samples come from populations with similar means, not the same mean. All right? The means should be similar, but not the same. To be the same would be an anomaly in nature. The means will be similar because there's still some noise in nature. All right? So if we're going to bootstrap ANOVA, and in particular the null distribution, which assumes the treatments were not effective, we must resample from mean-centered data. We cannot just mean-center the data. All right. So here is my ANOVA bootstrap. All right. Going to start from scratch, load the advertisements up, create the long form data that I need. Here's my ANOVA function. What is it doing? Let's take a look. For the null distribution of F, it's setting up this data set where each treatment data is mean centered and then resampled. The alternative values of F are simply taking the original treatments, 3 treatments, and resampling from them the original data. Okay. Then I'm running 2 ANOVA tests. One is for the null values of the data I should have if the treatments had no effect. And the second is the alternative values, which is the original treatments, resampling from the original treatments. Okay. So that's my boot ANOVA. All right. And I'm getting the 3 sales figures and I'm passing them to this replicate function. All right. You'll notice I'm passing the strategies or the treatment numbers in as a 4th parameter. There's probably a better way to write this. This is just the first naive way in which I'm going to be coding this, okay? So if I bootstrap this 10,000 times, wow, that's taking a little bit of time. There we go. Our null values of F are alternative values of F, okay? You will see now our null values of F are on average 1 because the F distribution should kind of peak close to 1. All right. This is my cutoff. It's about 3.17. I can plot the null values of F. That's an F distribution. The cutoff is about there. The 95% cutoff is there. So if the 3 treatments are not the same, I should expect alternative values close to this peak or close to about 1. All right. The mean will be 1. If my alternative value is greater than this 95%, then I should reject it. Here are my alternative distributions of F. I cannot plot them together because one is so short and wide, and the other is super narrow, and so this is my alternative distribution of F. Okay, I cannot really plot them together because to see this plot, it only goes to 10. My actual F value is 100 and something, so I can't plot them together. All right. All right. So that's just a recap of ANOVA, of simple one-way ANOVA, and how to bootstrap it. Okay. And again, the trick is always to think about how to set up the null, how to set up the world where the null hypothesis is true. In our case, the means are similar, not the same. They're similar. Okay. All right, cool. But again, the results are the same. We can definitely reject the null hypothesis here, right? And then the 2 distributions are shown here. Okay, so I hope this is a adequate recap of how ANOVA works and what it does. We'll be playing with it in some interesting ways in the next week. And after next week, we're going to kind of depart from hypothesis testing and things and we'll do something a little bit different. Okay, but we have one more week to kind of add one final story to the world of hypothesis testing. Um, I'm not going to go in much detail over the different types of ANOVA there are, blocking designs, factorial designs, and stuff like that, because this is not a design of experiments class. But I just want you to be aware that this is the simplest form of ANOVA is what we have seen today. Just remind you again that there are more complex forms of ANOVA. For example, there is randomized block designs of ANOVA. Let me just go through a story of a randomized block design. But before we do that, let's just take a stretch break, okay? Just relax. Done with simple ANOVA. Just a quick reminder of what block design looks like. All right. Okay. Um, and this falls under like design of experiments, okay? So let's read this other scenario that we've got here. And we'll see why this is a randomized block design, a different type of ANOVA design we need here, all right? So we're doing a study to measure the stress level of air traffic controllers. Do you know what air traffic controllers are? What is an air traffic, Meta, what's an air traffic controller?
Control the air traffic.
Oh, thank you, controls the air traffic. What would I do without you? um, where do you find them? At airports. Where in the airport do you find them? In the tower. So let's take a quick look at air traffic controllers. I assume we're not going to see people, but you will see that they sit in this tower on top, in this tower at the airport. That's who's sitting in there. If you weren't sure why the hell that tower is there, it's not a water tank. Okay, it's air traffic controllers. Um, and what is their job? Well, essentially, to this day, all the traffic of planes coming in and out of airports is controlled manually, not by a computer. Okay, it's controlled manually, and these air traffic controllers, they essentially communicate with the aircraft, and then they have a system on which they can see where all the planes are, and they have to like design the route each plane will take to get into the airport. Some of them may have to go in a circle a few times, some of them may have to take a particular way. They will guide them in one by one. Okay. It's an interesting. It's probably one of the few remaining places where we don't trust computers to do this yet. This is extremely complicated, and the decisions they're making are, for whatever reason, not entirely modelable in a deterministic way quite yet. More importantly, emergencies can arise where you need humans. Like the air traffic controller can tell somebody, okay, you need to turn to this angle, but they make a mistake. And the air traffic controller has to say, oh, no, 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 please correct, you need to go here. So the communication needs to be in real time, and you need to kind of correct for humans making mistakes, okay? And it takes a lot of intuition to do this. I'm telling you this story because there's another interesting fact about being an air traffic controller. Two interesting things. Two pieces of things you should know about air traffic controllers. One is good and one is bad. Which one do you want to know first? The good thing about air traffic controller or the bad thing? Okay, I'll tell you the good thing. The good thing is this is an extremely well-paying job. Air traffic controllers make a lot of money in most countries, especially maybe in industrialized countries. It's an extremely well-paying job, extremely better than professor at least probably. Okay. Part of the reason is because the risk is so high, and they need to be extremely qualified to be able to do this job. This is not a simple job, and they work on this their whole career to become good at it. Okay. Now the bad thing: air traffic controllers are believed. This job is believed to be the most stressful job there is. It's considered like in the top 5, perhaps, most stressful occupations that you can have. So money, stress, both. All right, so that's air traffic controllers. So imagine we're trying to reduce the stress of these air traffic controllers, and somebody, probably an IT person, has decided we can design the system they're using to be a little bit better, to give them some better information. All right. And there's a few different systems we can have. So there's a study measuring the stress level of air traffic controllers. And there are three alternative systems to consider that might reduce the stress of controllers. Okay. So there's three systems we would like to test. Now, we cannot do this experiment on hundreds or thousands of air traffic controllers because, first of all, we don't want to take that much risk, okay? So you unfortunately only have access to 6 air traffic controllers who are willing to test the 3 systems that you have. So 6 air traffic controllers, they're willing to come in, and on 3 separate days, they will try out one or of each of the 3 systems, okay? So it will look something like this. We have 6 air traffic controllers, and they will each try the 3 systems ABC. All right. So each controller will try A, and then B, and then C. Imagine on the first day, I ask all 6 air traffic controllers to try A, on the second to try B, on the third to try C. Reasonable? Is that reasonable? Unreasonable? What might be unreasonable about this? The traffic will be different maybe on the 3 days, right? So maybe the first day the traffic was low and system A looks amazing because it was a very low stress day. So that could be one problem. Another problem.
Like, for example, like kind of give the peculiarities of every system. So the controller will be already like expecting something from that system, maybe.
So are you saying the controllers will talk to each other or something else?
No, no, yeah. The controller will talk between each other.
So the first concern is the traffic, they will control it with talk with each other. That's easy to solve. I won't let them talk to each other. Or maybe I'll pick them in different airports. But there's a second problem you were just hinting at. What is it?
Is the like giving the peculiarities of every system.
Yeah.
Like, so the controller is gonna expect something from every system, so maybe contaminating the result.
Okay, right. So you also had an answer. What was it? Uh, Same. Say it in your words.
They will get used to the system. Like first they use the first one day, and when they go to B, maybe there are some similarities.
All right.
Or they're not used to system A.
Right. So maybe system A, it's like new to them, so they're struggling with it a little bit. But maybe system B is kind of similar to system A. I don't know. So it'll look easy compared to system A, especially because they got a whole lot of practice on system A. Okay. And similar thing with system C. Okay. Maybe by the third day, they're just used to handling different systems, and now they're much better at handling a new system. Okay. So for this reason, you cannot simply give them each system A, system B, system C, one after the other. Instead, what you must do is somehow randomize the order as well. So maybe one person does A, then C, and then B. One does C, B, A, B, C, A, like every like permutation possible. All right. So this is just one thing about um, block designs, and the reason it's called randomized block designs is because you have to randomize to a certain degree. What is the blocks? Well, we're not interested in understanding which controller is better or worse. We want to know which system is better or worse. Okay? And because we want to know which system is better or worse, we call the controllers, we just call them blocks. Meaning we know that there'll be some variability introduced because we have different controllers. They're not all the same people. So we just want to take that into account, but that is not our major outcome of interest. Okay? What we're interested in is these 3 systems. So we call these systems the treatments, and we call the controllers, in this case, we call them blocks. All right? So block 1 is the first controller, second controller, third, fourth, fifth, sixth. All right? And we make sure we randomize between we randomize between the systems so that the blocks don't have an effect. Okay. Now, what's interesting to me, and if somebody can explain this to me, I would be very happy. I don't really see the difference between them. They're just two variables, and essentially, you're randomizing between the controllers and also between the systems. So it's random all the way around. Okay, it just so happens that we call the variable we're interested in the treatment, and the other ones we're not interested in the blocks. Okay. And I just want to give you a quick rundown of how this works, and I'll show you some code, but I won't go into much detail for today because you don't have to do this for your homework assignment this week. You might have to do this for the week after, though. All right. So in a block design, just to make you aware of it, um, because we are now aware that the blocks will also have some kind of effect, meaning the 6 controllers will respond to the systems differently because they're different people. So our ANOVA structure will look a little bit different, okay? And just to give you a quick rundown here, the treatments, okay? The treatments will look like this. The variability between the treatments will look at, first of all, some letters. K is still the number of treatments. 3, B is now the number of blocks. We have one set of blocking variables, okay? And what we do is we look at to get the treatment variance, we look at the three, excuse me, x dot j. So j goes from 1 to k. So we're looking at the result of system A versus system B versus system C, right? We're looking at the mean effect for this, for the mean deviation between the scores here and the grand mean, and we're summing and we're squaring and summing this up for the 3 systems, okay? And we're doing this, I'm getting a little confused here. And then we're multiplying by the number of blocks that we have. Um, so let me see if I've got this right. Okay, no, I'm sorry. It goes top to bottom. I'm sorry. It goes top to bottom. So we're looking at these numbers, 15, 14, 10, 13, 16, 13, and we're summing and squaring them. Their mean will be this, 13.5, and then the grand mean is 40. All right? And we do this across the 3 systems. Excuse me. So we do column-wise across the blocks for one system. We compute the mean for that system against the grand mean. We sum it up. We square and then we sum it up. And we do this for each of the 3 systems, okay? Column by column. That gives us, and when we do this, it will give us the variability and the mean, or the variance, the variability and the variance of the treatments, the variance due to the treatments. Then there's variance or variability due to the blocks. The different controllers will have different effects. So what we want to do to take them into account is we'll go row by row through each controller and we'll compute their mean for controller 1, controller 2, controller 3. We'll compute all their means, see how these means differ from the grand mean. The grand mean is the mean of all our data, okay? And we will do this row by row for all 6 blocks. And this will give us variability, the numerator, for the blocks, and variance when we divide by degrees of freedom for the blocks. Okay? And then we can do a couple of interesting f-test. Oh, and by the way, the error will be simply computed, the error variability will simply be computed as the variability of the treatments minus, the variability of the total variability minus the variability of the treatments minus the variability of the blocks. That gives us the error variability, the numerator here. We divide by degrees of freedom to get the error variance. Okay. And then we have the grand variability here. The total variability is simply each of these each cell minus the grand mean. All right, squared and summed. All right. The reason I'm telling you about this is to make a couple of points. One is, you notice the way we're doing it is we're computing variability of the treatments and variance of the treatments, variability of the blocks and variance due to the blocks, right? And then we have to compute the error variance. You notice that we're not simply taking total variance minus treatment variance minus block variance. We're not doing that. We're not subtracting the variances from the total variance. We're doing it the other way around. We're doing it by variabilities. We are computing the total variability and subtracting the variabilities of treatment and block from the total variability, right? Why are we doing it this way? Why don't we just subtract? Because we are only interested in the variances. Why don't we just subtract from the variances? And this is something that puzzles many people until you realize variabilities add up. The total variability is actually equal to the treatment variability plus the block variability plus the error variability. Okay? However, variances don't add up. Variances, if you take the treatment variance plus the block variance plus the error variance, you're not going to get the total variance of your system. All right? Why is that? The reason is in the degrees of freedom. When you divide each of these by a different denominator, they're not going to add up to the total variance. Okay? So that's one of the reasons when we talk about dispersion, I keep talking about variability and variance. They're both useful. Variabilities have this nice property that they add up to the total variability. Variances do not do that. Okay? Even though for our statistical tests and the distributions we want to deal with the variances, not the variabilities. Okay? When you divide variances, they have this nice F distribution. Divide variabilities that do not have a known distribution. All right? I'll just briefly show you the R code, but I won't go into much details about it because I think I'll spend a little bit more time next week talking about it, perhaps. Okay, so in this case, we want to do ANOVA, and this is a randomized block design. All right. So if we did not take the blocks into account, if we did not take into account that the 6 controllers are different people, they're going to respond differently, then this is what our code would look like. We would just try to say, how is the stress due to the different systems? All right. And then we would do, this would do an ANOVA test for us, and it would give us an F value of about 3.2. All right. However, if we take the different controllers into account, then our model looks like this. We're saying the stress felt by each controller is due to the stress of the system plus their own individual differences between the controllers. This is our blocking variable. So now the ANOVA reports to you the F value comparing the system, the variance between systems versus the error variance. That's this F value. This F value is these two numbers divided by each other, 6 and 1.9. It's the variance between the controllers divided by the error variance. That gives us this F value. Okay. So this tells us that the system has a significant effect on the stress levels because the F value is bigger than, let's say, the threshold such that the p-value is less than 5%. But also we notice that the controllers, that a lot of the variance comes from the controllers themselves, from the people taking part in these experiments. They are contributing variance as well because they're different people. All right. And the error and their variance is not significantly different from error if at the 5% level, but it would be at the 10% level. It's still quite a sizable amount of variance. Okay. So this is an example of block design. And then you can do an interaction plot. The code is right here to kind of have a look at how these 6 controllers, how they performed on systems, let's say A, B, C. Okay. Where you see each of these lines belongs to one of the controllers, so you can kind of see how they responded to the 6 different systems. I'll go over this in more detail maybe next week, but I just wanted to put this in your ear so that you don't think that we're only going to do that. We only have one-way ANOVA. For those of you who are going to do more interesting experiments, we can do block designs and other things that we'll see next week. Okay. However, the good news is for this homework assignment, I will not get into block design. I will only kind of focus on one-way ANOVA and bootstrapping it. Okay. All right. Before I let you go, a little roadmap. Where are we going after this? Once we're done with ANOVA, what are we going to do? MANOVA, something else? Um, we're going to end this little section on hypothesis testing with next week by just recapping everything we've learned about t-tests and bootstrapping and f-tests and bootstrapping of f-tests and bootstrapping ANOVA. And we're going to talk a little bit about what is error and what is statistical power. And we're going to do these again through some simulations to understand what these concepts really mean. All right. After that, we're kind of done with statistical testing, parametrically and non-parametrically, through classical statistics and using the bootstrap. After that, we're going to have a section on just, we're going to start after this, we're going to start talking about the geometry of data. So I promised you in the beginning of the semester, one of the things this class will do is not only the computational approaches to data and data analysis, but also the geometry of data and how to understand data from geometric view perspectives, not just statistical perspectives. So after next week's class from week 10, if we have class on week 10, I don't know how many holidays we have left, after the next week, we're going to take a completely different look at data from a geometric point of view rather than a statistical point of view to see what does that exactly mean. All right. And after that week, we will use both statistical and geometrical views of data moving forward beyond that. All right. Okay, cool. So that's all enough for today. Hopefully the last assignment will not be too difficult because now you've gotten very used to doing classical hypothesis testing and bootstrapping. It should be about the last time we do that. Okay. All right. Thank you so much.